We just implemented a self-attention mechanism with a causal attention mask. Now we are almost done with the self-attention mechanism that we are going to use in the LLM. There's just one more thing we are going to add, and that is the so-called multi-hit attention. So if you are familiar with the attention is all you need paper, shown here, this is the original paper by Google in 2017 that introduced the original transformer architecture. So LLMs like GPT and so forth, they use this right subpart here, which is also called the decoder submodule. So the left part is not commonly used anymore in LLMs. So this was a more, let's say, complicated architecture than was really needed. So on the right-hand side, this would be what's similar to GPT-style LLMs today. And you can see there's something called a masked multi-head attention module. And that is what we are going to implement in this section. So before, the causal attention module would be the same as masked attention. So masked here is a more general term that refers to a type of masking. In the previous section, we introduced a specific type of mask, the causal mask. And by the way, they were also using a causal attention mask. But yeah, whether you call it masked attention or causal attention in this context is the same thing. But our causal attention class that we implemented, it would be a single head attention module, a masked single head attention module. Now we are going to implement a multi-head attention module. So a multi-head attention module is similar, except that we have now multiple single head attention modules stacked on top of each other. So if you are familiar with convolutional networks, just to draw an analogy, so a convolutional network is an older type of architecture that has nothing to do, or it can be used for text extraction, but it was originally also designed for image extraction. So if it's unfamiliar to you, maybe don't worry about it too much. But the idea was that we had we still have and still use this type of network to extract different types of information from an image automatically. And there are so-called channels here. So or different filters. So the different filters extract different types of information from the image. And in that sense, that's what we are also trying to accomplish here. We have multiple heads or multiple of these self-attention modules to extract different types of information from the input. So the idea is really to extract more and different types of information. And this works because each single head attention module is initialized with a different set of weights. And then each of them will learn slightly different features during the training. And then it's a way of extracting more and more diverse information from the input. To show this to you in a visualization here, so maybe, let me see if I have a simpler figure here. So before we had this inputs tensor, where inputs was a 6 by 3 dimensional tensor, we had 6 tokens, and then each token was embedded in a 3-dimensional space. And then what we did is we had a single head attention module, the causal attention module, that created a 6 by 2 dimensional context vector. So the context vector still had 6 numbers of tokens, or 6 rows corresponding to the 6 tokens, but each row was a 2-dimensional embedding now instead of 3 dimensions. We said before the 2 and the 3, they are arbitrary, we can choose them, but to keep things simple, let's assume we had 3 input dimensions and 2 output dimensions, and what came out was this tensor Z. So here it's called Z1, so just think of it as Z. Maybe to also show it to you here. So our input was a batch consisting of 2 input examples, and this first one would be the inputs X. So here we have the 6 rows in the 3 columns, the 6 rows corresponding to the 6 tokens, and the 3 columns corresponding to this 3-dimensional embedding. And then the context vector that we got out of the causal attention mechanism was also 6 by 2. Also, we had 6 numbers of tokens, and now 2 dimensions as outputs. So before it was 3, now we have 2, but the number of rows is the same. Anyways, so we had that. Now we are going to create a second context tensor. So before we only had Z1, now what we are going to create is Z1 and Z2. So this would be a case where we have two heads, so 1 and 2. The number of heads, it's arbitrary. It's a hyperparameter. For example, in GPT-2 models, I believe it's between 16 and 25. We will see actually exactly how many there are in chapter 5. But yeah, we usually use more than 2 heads. Here, I'm just using 2 heads for visualization purposes, so it fits nicely onto the slide. And then, yeah, we create 2 of these context tensors, and then we concatenate them. So you can see we have 2 context tensors where each has an output dimension of 2. And when we concatenate them, we have now an output dimension of 4 because it's 2 times 2. And this is what we are going to build. And how we are going to build that is by simply stacking 2 of the single causal attention mechanisms that we implemented in the previous video on top of each other. So in the previous video, we had the causal attention mechanism that had a weight matrix for the query, the key, and the value outputs. And then each the query weight matrix created the queries, the key weight matrix created the keys, and so forth. Now we have a second set of weights. Before we had only WQ. Now we have WQ1 and WQ2. So we are having a second stack. You can simply think of it as doing the same thing twice almost and then concatenating. So at the end, we have also 2 context tensors like mentioned before, and we create this combined context tensor. So let's maybe see how that looks like in code, because I think that will make things a bit more clear. So what we're going to do now is we are going to create a class. Let's call that a multi-head attention wrapper, and then we use the torch module here. And then let's do the init constructor. Self. And here, one thing, just sometimes tend to forget that we are just inheriting the features from the module class. Oops. And then one thing is we are going to implement this in a simple way for now. Later in the next video, I will show you a more efficient way, but the simplest way would be really just stacking these causal attention mechanisms. I will just copy and paste it from the previous video. So previously what we had is we had this causal attention class, and we are now instantiating an object from this class. Let me add the missing parenthesis. So we are instantiating this object, and we are going to instantiate it a number of times. So for example, for a number of times where the number of times is determined by the number of heads. So for example, if we set the number of heads to 2, let's add it actually here. So the number of heads could be 2, and then this would be creating 2 causal attention heads. Let me also copy those over actually. And then also the QKV bias. We're not going to use that one, but just for completeness. So that is how we initialize, or how we would, for example, initialize multiple of our causal attention modules. One more thing though is in PyTorch, let me just make this a bit nicer. In PyTorch, I recommend using the nn.module list here, because it will give it some nice properties with the buffers and everything I mentioned before. And so this would be now a stack of multiple causal attention classes or objects of this class that we implemented in the previous video. Now let's actually define the forward method to use that. So the one way, of course, we could use that is by just calling head on the input for each head in self.heads. So this is a list of multiple single head attention mechanisms, and we're just iterating over those. So let's make this a list. And in PyTorch, the simplest way to combine them would be concatenating them. So we do that along the last axis here. And this should be giving us our concatenated context tensors. And this is really all there is to it. I believe if we looked at the figures, it looks a bit more complicated because there's a lot of stuff going on. So each layer here is showing the causal attention mechanism, but really it's just multiple of those on top of each other. And we already did the hard work and implemented this. So we are just stacking it here. Then let's actually use this torch manual seed, just so to make sure you get similar results. Let's just define some variables. So the context length would be batch.shape1, because we have the batch 2 times 6 times 3. So we have 2 inputs, each has 6 tokens, and then the output dimension or input dimension of each token is 3. And then we can also define the input dimension here again, and maybe also the output dimension. So the input dimension is 3 in the figure, or we can also make it more general. But shape can extract it from the input, and then let's say for the output one, we do 2. And again, like I mentioned, this is a hyperparameter. So we will use much larger values later on when we implement the whole LLM. But let me code this one. And I'm just going to copy this here. So we have defined those. Dropout, let's just, for simplicity, set it to 0. And yeah, this is technically it, and I hope it works. It does not. Super needs an argument. Yeah, I always make a mistake here. I think I just forgot the parentheses. And now the shapes are not aligned. 12 by 3 can't be multiplied by 2 by 2. So I think I made a small mistake somewhere. Queries here. So let me see. I can see I should have written a different number. I should have written -1 because we want the 3 dimensions and not the 2 dimensions here. So that was the mistake. Yeah, so this is it. Yeah, I could also just write 3 here. And this should work. Now we have this multi-head attention mechanism. So the first 2 values here, they correspond to the first context vector, and the second one to the second. So what we are doing here is we're creating these 2 sets of tensors, and then we are concatenating the results. And this is, yeah, really it.
Get this book at manning.com.